Okay, welcome back, everybody. And the topic today is first to have a discussion of possible paths for project number 2. And then we are going to dive into Fourier transforms. And from the experiences for last year, I decided to give a kind of review of Fourier transforms first, because there are many people who have not studied that in their mathematical physics courses or math courses. So it's a very kind of compact introduction to it so that you get an overview. But I wanted to give you some of the basic motivations for Fourier transforms and why quantum Fourier transforms are so interesting. It's actually a pretty important algorithm. So let's just enter the full screen here. So the project number 2, as usual, is something which we want to be as flexible as possible. And I know that there are groups of people who would like to implement QFTs and study the phase estimation, the quantum phase estimation algorithm. So this is something you can use both for finding eigenvalues. So one possible path is, if you are familiar with fast Fourier transforms, which is the algorithm, the classical one for performing Fourier transformations, you can compare the QFTs with the fast Fourier transforms and have a discussion, a pretty broad discussion about those properties. So it could be just what you might call a very mathematical path. The other one, if you want to pick up the thread from project number 1, you can then implement the QPE, which was the first algorithm which was proposed, which ends up with very lengthy computations, and it's not very efficient. And but that's something which is then useful if you want to make what we might call a theoretical sum. Now, quantum phase estimation and QFTs by themselves can make up one project. And we had several people last year who did that. But then the kind of pinnacle here is Hjorth's factorization algorithm, which is essential for, factorization of large numbers. So it depends a little bit on how far you get, but this is definitely one possibility. And we have from last year, there is a participant in the course who, by different reasons, could not finish the course, who is an expert in number theory, who's actually looking after partners. So I don't mind if you have larger groups. This is very much up to you if you find this an interesting topic. So then we also have the other algorithms, and you may need quantum Fourier transforms. So quantum Fourier transforms is a kind of backbone for many of these algorithms. And obviously, if you wish to study other algorithms, please feel free to suggest other possibilities. Now, for the VQE, if you're more into quantum mechanical simulations, if that is what is of interest, then there is something which is called the adaptive VQE, which moves a step further and often gives much better results than the standard VQE. And this is something which could then be applied to, let's say, the Lipkin model. You could generalize this to more than 4 particles. But alternatively, you could also move into the calculation of more interesting physical systems from atomic physics, quantum chemistry, etc. So that's another path. And then we have quantum machine learning projects. There is one on Boltzmann machines, another one on quantum neural networks. So I will discuss the QPE and quantum Fourier transforms till the break before Easter. So that's essentially the plan. And then you will get all the material which is needed. So today I will roughly discuss the basics of these algorithms. And next week we are going to look at the quantum phase estimation algorithm together with implementations. So you get a feeling of what is needed to be implemented. And clearly, if you have other ideas, other things you would like to study, feel free to suggest them. For some of these topics, it may be more efficient to use something like Qiskit or QBraid or PennyLane, etc., which are more, how to say, you have ready-made functions for doing specific things. So you don't need to write everything from scratch yourself. Although last year we had many groups who actually did the QFTs and the QPEs from scratch. Because you have, essentially in project one, you have developed your own algorithms for setting up gates, for setting up qubits, initial states, and so on. So this is a rough sketch of possible paths. If you have other ideas, please shoot me an email. And if you have some suggestions now, I mean, feel free. There is a short description in the projects. And I outlined essentially the first points. And then for other ideas, I mean, this is something we can discuss. Okay. Okay. So the idea now is to give you a brief reminder of Fourier theory, which is, if you come from a field like signal analysis or similar topics, or you've been studying harmonic oscillations, then Fourier analysis plays a central role. If you're doing convolutional neural networks, I mean, Fourier filters are some of the more popular ones in machine learning. So this is a field which is simply huge. And you will find dedicated textbooks and even dedicated university courses on only Fourier transforms and Fourier theory. So we are mainly going to use some of the basic ideas here to switch after roughly 1 hour now in the next lecture. We are going to switch to quantum Fourier transforms. But it's okay to have seen and understood what a Fourier transform is doing. So the QFTs, they are the quantum analog of what's called a discrete Fourier transform. And as we mentioned, they play a central role in this quantum phase estimation algorithm and also Shor's algorithm. And if you're interested in encryption, in factorization, this is one of the central algorithms in quantum computing. And it's the one which made all people who deal with securities, encryptions, and so on to tremble back in '94 when it was presented. Because people fear that all their encryption algorithms could then be broken. You know that, you probably know that, but many of these encryption algorithms are based on your capability of factorized numbers. So they also provide an exponential speedup over classical Fourier transforms. And this is one of the things which makes them very, very advantageous. So if you're going to give a seminar, although this requires that people have some feeling about Fourier transforms, one of the big advantages of machine learning, quantum computing, is actually in the power of quantum Fourier transforms. So the typical discrete Fourier transform, as you will see later now, if you just encode it as it stands, it's a unitary or orthogonal transformation of a given basis. And that is essentially a matrix times a vector. And if you have a matrix of dimensionality n times n, that requires n squared floating point operations. Then we have the popular algorithm, the one which is ranked as one of the top 10 algorithms in the last century, and is still ranked as one of the top 10 algorithms, and that's the fast Fourier transform. And that improves this to n log n. And then the QFTs, they reduce the complexity to log n squared. And so if you use quantum gates, and this is what we are going to discuss in this series of lectures before the break, the Easter break. So the act on a superpositional state, it's again the superposition, which is the big magic, which makes the quantum Fourier transform superior to any of the other ones. So that means that we are processing all inputs simultaneously. And this is crucial in algorithms like Shor's and the quantum phase estimation, if you want to evaluate eigenvalues. So that's one of the paths for the second project. That is you implementing a quantum Fourier transform, then doing the quantum phase estimation and comparing with the VQE. It's very simple. And if you think back to the gates which we have been discussing, you have encountered the control X, the control C, the different phase gates, etc. So this is normally done by a Hadamard gates. So you get the superposition, and then you have a controlled phase gates. And you're going to see that in the algorithms. But these are the only ingredients which we need. And if you do a 3-qubit QFT, that uses only where little n is a number of qubits. So it's pretty efficient for quantum hardware. We have mentioned Shor's algorithm, the quantum phase, and then we have quantum signal processing, which is one of the big fields of applications. So on the spectral analysis of quantum data, and that becomes also important for AI applications of quantum algorithms. Then there are topics which I will not cover. This is about the QFT, how they store the information, and also the number of qubits which are needed for specific type of transformation. So the N, uppercase letter N in the notes here, is going to represent all the possible realizations. Because if you have a bit-based system, bit 0 and 1, if you then have n qubits, then the possible number of realizations which you have is 2 to the power of n. And this n then represents all the possible states. So if you have 2 qubits, you can then have the state 0, 0, 0, 1, 1, 0, and 1, 1. So that's 2 to the power of 2, which is equal to 4. So that's the number of transformations which you will get. So about the reduced memory complexity, something which we will not handle, and also what's about the quantum signal processing is also something which we will not discuss here, because this is way beyond my area of competence. So I would not be able to say anything meaningful at all here. So if you want to have a brief summary, they provide exponential speed up. That's one of the selling points. They enable quantum algorithms like Shor's algorithm and the quantum phase estimation. They are more efficient in memory usage and circuit complexity than classical methods. And there is a huge potential of these algorithms in signal processing, AI, and cryptography. And they will rely heavily on QFT. And some of you are doing your thesis work in these directions. So this the QFT is actually the backbone of what you need as a starting point here. Now, I'm going to use the slides a little bit on Fourier transforms. I hope that's okay. So just to remind you of that. So how many of you are familiar with Fourier transforms? 1, 2, okay. So last year we had actually very few who had ever seen a Fourier transform. So I actually needed a double lecture on Fourier transforms, but hopefully now we can speed up a little bit. So one of the classical fields of applications is actually harmonic oscillations. So if you look at the classic Newtonian equation of an object which oscillates harmonically, if you take away the external applied force F of t and a velocity-dependent term, which is responsible for damping of the motion, then you would just have harmonic oscillations back and forth. Nothing happens, just back and forth. If you add this velocity-dependent damping term, often called a friction term or just damping term, then you will damp the motion and the object will come to rest, unless you apply an external force. These type of systems can then be expressed in terms of a Fourier series, because the solution is essentially a linear combinations of sines and cosines. So this is a typical example where Fourier theory has been applied to the solution of differential equations. And I know that some of you come from a partial differential equation world, and in that world, Fourier transforms play a central role. So if you have some kind of external driving force, you can now always find a particular solution to that differential equation for each of these terms f of n. And then the particular solution for the entire driving force is then given by a series, which then runs as a linear expansion of this one. So superposition is especially useful when this function f of t can be written as a sum of the sine terms. And the driving forces, another nice feature is that they are periodic, which means that they repeat themselves. And you would typically then have some period t, and this after some time t, our function repeats itself after this specific period. So one example, which you may have seen, which you can approximate with a series of sines and cosines, although you will get wiggles on the corners because this is a discontinuous functions. So if you fit a continuous function with a Fourier series, even with a discrete expansion, this will always be a continuous approximation. So if you have a discontinuous function, which is still periodical, you will get some kind of wiggles and you will need a large set of Fourier coefficients to actually see that. So you could see that now if we go to a, so let's just go back to the Jupyter notebook. And this is going to be one of the few cases we're going to look at the Jupyter notebook today. So a typical signal, which many of you may have encountered, is something like this. And this is something which repeats itself regularly in a periodic way. And you can try to fit that with a Fourier series. And in that specific case, if we would fit this with some expansions in sine here, I'm coming back to this in the slides, but I just wanted to show you a specific fit which you could make then, where you have a general one, a cosine and sine. This is typically expressed in terms of exponentials. And then you would have an exponential series where you sum from minus infinity to plus infinity. These coefficients are complex, the CKs in general. And we are just going back to that and see how we can find them. But let's now look at the fit here before we go back to the mathematics. And there should be now the square well case here. And if you look at this one, so I'm setting up again the same 500 points. It has an initial start time, 0 and 1, a period of 0.2. There is a width of the signal, etc., etc. And this is what it would look like. And if you blow this up, you will see that there are some wiggles at the corners here, because we are using a continuous function to fit a discontinuity here. So we would need actually a pretty large basis of sine and cosine functions to get a fit here. So let's just go quickly back to the slides and go through the Fourier part before we then move into quantum Fourier transforms. And then I'm just basically going to use the whiteboard for the rest of the lecture here. So let's quickly go back to the whiteboard. No, not the whiteboard, but the slides. So I should have them. So let me just bring them up just a moment here. Sometimes when, okay, let me just share it again. So you saw these simple examples, and I'm going to take the liberty of now just going through this by slides. Since many of you are pretty familiar with it, I'm going to go just spend roughly the lecture here. So Fourier's idea was actually to expand a continuous and periodic function in terms of sine and cosine ordered functions. So you could think of something like that, where you have these unknown coefficients. And one of the assumptions you make is actually that this function f of t is bounded. That is an important assumption, because else you cannot prove the stability criteria for the Fourier expansions. So what I want to simply to show you now is this playing around with finding the coefficients. Because when we set up the quantum Fourier transform, we are simply going to look at these coefficients as the coefficients of a unitary transformation. So you would typically rewrite, as we mentioned in the Jupyter notebook, this series as a sum of sines and cosines, where you would have these coefficients here. And in principle, this series is an infinite series. And you saw that with us trying to fit a discontinuity that you would need, if you were to play around with that with less terms, you would actually see that the reproduction of the data is not that good. So if you take that Jupyter notebook and you just reduce the number of terms in here, you will just get results which look worse and worse. So then the standard trigonometric relations, if you use those, you can then rewrite this in terms of a new series where you sum from minus infinity to plus infinity. And these coefficients are in general complex ones. And then you can also, sometimes you will see it rewritten in terms of the real part of the exponentials, and where we simply use the properties of these coefficients here. So I just leave that as an exercise to show that. That's just a manipulation with sine and cosine functions. So if we now have a periodic function, we could make this assumption here. And the question then is, how do we define, or how do we find this coefficient C? So the typical trick is actually to multiply the left-hand side and the right-hand side with a factor like this. And then you isolate the term with CL here. So where you perform this multiplication, because then you see that if you multiply and look at this sum here, there's a term where you have the exponential of minus 2 pi ILT times e to the 2 pi ILT. So if I isolate the term with L, then I just get this term, just CL, and that's given by this term minus this term here. And then we integrate over the period. So we assume that we have a period of 1, but actually these equations here can be shown to be general for any period. So period of 1 here is just simply a choice I made, but you can actually generalize this one to any other period. So this is you having just scale data. So if you look at this function here, the one you integrate away, because what happens then is due to the properties of these exponential functions that all these other terms, when k is different from L, is 0 when you integrate up. And that's pretty straightforward to see. When you just perform the integrations here, then you will get terms with e to the 2 pi I times k multiplied with e to the 2 pi times n. And then in case n and L are different, you will get that the integral here simply gives you 0. It's pretty straightforward to see that. So that means that we can define these coefficients, and it's common to actually call this the Fourier transform. And then you would label these C's with a function f, with either a tilde or hat. This depends on your taste, guys. And then you would simply have the so-called Fourier transform of the function f of t. And then you can also define the inverse Fourier transform. And here we show that if you now, instead of a period of now 1, you have a period of a, then when you add one period, then this should be the same. So in the previous case, we just put the period to 1, and then you can show that the a, if that a is any number, and if you take the derivative of this equation, what you get then is simply this expression here, which gives you 0, and where we use the periodicity. And then since that shows that the expression for f is actually independent of the period. And a common instance is actually that you integrate from -1/2 to 1/2, or minus L to L, or any period which you would prefer. So you would typically often get something which runs like this, where you would have a period t, which you define, and then your function is then periodic as a function of this number pi here, which often is just 2 times pi. So if you do that, if you introduce new variables, you can then simply define these coefficients. So you would have a gk of t. These are actually called the so-called harmonics. So you can then, if you then set it up, you can define a general expression for the Fourier transform, where you have the Fourier transform of a function f of t in a general period t here. And you can change then from minus t/2 to plus t/2. This is very much up to you. And this 1/t, which you see here, is simply a normalization constant, which comes out from the integration. So this is the standard expression which you will encounter. And for those of you familiar with differential equations, if you take something like a second order derivative, then when you transform that one, the differential equation, that if you have something like the diffusion equation is an equation you can solve analytically when you perform the Fourier transform, because then you just get a constant, which could be k squared, which then represents the kinetic energy term, and that is equal to your function to the power of t, of time, and then you can integrate immediately the equation, and then you have the solution. which in that case is going to look like a Gaussian. So that would be the solution with a Fourier transformation of the diffusion equation in one dimension. And then you can do that in 2 and 3 dimensions, and you will still get the same type of solutions, which would be a Gaussian, again, in more than one dimension. So the typical then choices which you could find are, this is very much up to you, what kind of choices you want to make. And a common choice, this is actually a pretty common choice for this harmonics, is often to define it like this. So that's a pretty common choice. These are just choices which you can make here. And then if the signal function is real and even, then you would typically have that f of minus t is f of t. And that often simplifies. And if f is an even function, then f is also an even function, which leads to this property here. So these are things which we will carry with us when we look at the quantum Fourier transforms. And for the sine example, then the typical period is 2 pi divided by the frequency. And higher harmonics can also satisfy the periodicity requirements. In general, any force, if you look at this differential equation that satisfies the periodicity requirement, can always be expressed as a sum of these so-called harmonics. Now, in the code which you saw, what I was implementing was a signal, which was just this square well signals, pretty simple ones. And these are signals which you could simply set up as a value 1 when you have half the period, and minus 1 when you have the other period. So this could be a typical example of a function. And then if we integrate from t equals 0 to 1, we have a nice analytical expression, which would then give us, for these coefficients, when we perform the transformation, it gives us these coefficients here. Now, this is 0 when n is even, and 2 when it's odd. So that means that when I use the sine function, I can actually rewrite it like this in a very compact way. So for my square well signal, I could simply approximate that one with an infinite series of sine functions. This is essentially what I did in that second code. That's basically what I implemented. And if you have very few sine functions, you will get a pretty bad reproduction of the square well. You will see always some wiggles, but they will become less and less pronounced when you have more and more terms. But for this specific signal, which is discontinuous, since you're trying to fit it with continuous functions, to get an acceptable reproduction, you will need in the thousands of sine components to get an acceptable reproduction. This depends on how you define the error. So if you're happy with 100 sine functions and a larger error, then you would do that. And if you're familiar with Fourier series, you also know that there is an error function, which you can estimate on the, the convergence criteria of a Fourier series. So this is the code which we discussed. Other things which are very important is actually typically the inverse Fourier transforms, which is then often written like f to the minus 1. And then you can also have the inverse Fourier transform, the product of two functions. And that is often written like this. And you're probably familiar with convolution. And for this term, which you have here, of two functions, this will be written like that. And this is typically the convolution of functions g and f. So this is a pretty rough course in the standard continuous Fourier transforms. We'd also have the discrete ones. But in some, if you look at it, these are the expressions which we often end up dealing. So we have a function in the k basis. So we perform a transformation to the x basis. And then we have f of x here. And then we have the inverse Fourier transform. So the way we are going to interpret them, as you will see when we now introduce the quantum Fourier transform, and also the discrete ones, is as a transformation from one basis to another basis. That's essentially what this is going to mean for us in the technical terms. Feel free to ask questions. I mean, I know it's a pretty rough overview of Fourier transforms, but this is something which we need to deal with. So if we now change notation, we can replace this. I'm going to replace this t with an x. And then we are going to make another generalization by having a discrete functions. That is, this f of x goes over to f of x of k. And x of k then is given by some k times delta x, where these values of k run from 0 up to a specific number. And then this leads to a sum which looks like this. And then the transform is given by this function here. This could also be a set of numbers if you want to. So that's a discrete one. And typically, you would see it written down in this very compact form. And as we said previously, these harmonics often are scaled with 1 over the square root of n here. That's a pretty normal scaling. And this is a standard expression for what you see. So let's switch over to the whiteboard and look at the discrete Fourier transform first. And then we move over to the quantum Fourier transform, which is just another variant of a discrete Fourier transform. But as we said in the beginning, the advantage here is that the discrete Fourier transform, the way we are going to derive it, is going to be given by a matrix, a unitary or orthogonal matrix, times a vector. And that requires, if the matrix has dimensionality n times n, it's going to require n squared floating point operations. The quantum variant of this is going to require log n squared. And that is a lot of less operations than the classical direct implementation, if we skip the the fast Fourier transform. Okay, so let's switch over after this very, very quick review of Fourier transforms and Fourier theory. But these are the ingredients which we need when we are looking at the quantum variants. So if we now look at the definitions here, and let's try to write this out in terms of the vectors which we are used to. So the way we could do this now is simply to set up this vector x, the way we have written it before. And I'm going to put a vector sign on top of it because my boldface on my lecture notes is not always clear enough. So we are going to use this Dirac notation anyway. So this is going to have components x0, x1, down to xn minus 1. And the xj's here, xj's, not that one, xj's. These are in general complex numbers. They don't need to, but they are in general complex numbers. And when we do quantum mechanics, they are complex numbers. Then we could think of a specific component then of y of k, which is now given by a transformation of, so this is the Fourier transform. This is the discrete of j equals 0 up to some n minus 1. These are the components I want to transform. And this is given by a 2 pi of I. And then I have my j times k divided by n here. So this term, the exponential multiplied with 1 over n, is what we call this kind of harmonics previously. So this is just a discrete variant of the continuous function which we looked at earlier. So this means that we can define a vector y, which now will be given by all these different components. So there will be a transformation from x0 and up to xn minus 1. So there's going to be a j equal to 0 up to n. And then we can put outside 1 over square root of n here. And here we're going to have an x of j of e to 2 pi I. So this is the imaginary I. J is just a summing variable. But then this is multiplied with 0 because this is the component with k equal to 0. So let's just mark that one. So this is y0, and then we have k equal to 0. Then we have the next component, which obviously has to be y1. And xj of e to the 2 pi of I, we have j multiplied with 1 divided by n. So this will be the term with the y1. And this continues all the way down to the last term, where we have j equals 0 to n minus 1, and then xj of e to the 2 pi of I of j. And then we would have a term now, which runs like n minus 1, because that's the last term. So n minus 1 divided by n here. And this term, which you see here, that is the term which we would call y of n minus 1. So this would be k equal to 1. And here we would have k equal to n minus 1. Then we close here. So let's look at a simple example to get acquainted with these type of expressions. So if you then look at the case, simple example, we could then define X transpose as 1 and 2. So this component will be x0, and that component here is x1. So if I put k equals 0, what I get then is that y0 would then be given by 1, I'm just using that formula, plus 2 divided by square root of 2 here. And then I would have, for the next case, k equal to 1, and then I have y1 is going to be equal to 1 over 2 pi plus 2 divided by square root of 2, and then I have e of I pi. And we know that that is equal to minus 1. So this term here gives us minus 1. And if I now look at my transformation, which I'm doing, we can then write this vector y in terms of a matrix U, which acts on X, and where U is given by 1 over square root of 2 here, and then I have 1, 1, 1, minus 1. So I picked up this simple example here because this U here is nothing but the famous Hadamard gate. And you're going to recognize then when we now look at the quantum Fourier variant of the same transformation. Okay? So it's often useful to look at these simple examples. And we know also that if I take u of t, that is given by u of t, and it's given by the identity matrix, the 2 by 2 identity matrix. So you can think of this as an orthogonal transformation here. And that's what actually these discrete Fourier transforms are. So they can compute it much faster as a quantum components than on quantum computers and on classical computers. And the QFT has, as we said, has pretty important consequences when it comes to the factorization of large numbers. We also use this one for the quantum phase estimation to extract eigenvalues. And it's also used in many, many other algorithms. So essentially, if we now look at what we have, you could think of this in terms of another example. So let's look at that. If you now think of something slightly different, so this is a small digression. If you think of a polynomial expansion, then we know that this f, a specific function at x of I, is normally approximated by a polynomial of degree n minus 1. So you have n points, and then we could fit a polynomial up to degree n minus 1. And this is something which would then be equal to a sum over some aj of x of I to the power of j. And these j's go from 0 up to n minus 1. unless we truncate the order of the polynomial. We don't need to use all the points, because you know that if you have 10 points, you can fit up to 9th order polynomial. But you could truncate that earlier, because if your function is a quadratic function, there is no point in fitting a polynomial of degree 9 to reproduce a quadratic function. But let's just write it out, because this has some parallels to what we are doing now. So we would have xi to the power of 0. This is just the intercept, xi plus a2 of xi to the power of 2, and then plus plus. And then we end up with some n minus 1 of xi to the power of n minus 1. So it means that we could now write, suppose we just call this p of x of I, just to simplify. So it means that we would have a polynomial now, which is now given by this p of x0, p of x1, and down all the way to p of xn minus 1 here. And this is actually given by some matrix multiplied with a vector a, where a is this vector with the unknown coefficients a0, a1, up to an minus 1. So this v has a famous name. So if we now keep all terms, so this is often a real matrix. So this is an n times n matrix. And in the literature, there's a famous matrix, which some of you may have heard of, van der Monde matrix. So the v is then given by, if we now look at it, this is given by 1, 1, all the way down here. So these are all 1s. And then I have x0 to the power of 1, x0 to the power of 2. And if we go all the way up, we have x0 to the power of n minus 1, x1 to the power of n minus 1, down to xn minus n to the power of n minus 1. And here we would have xn minus 1 to the power of 1. And this just repeats itself here, this pattern, which you see here. So this is the famous van der Monde matrix. So essentially what we are doing then is that this is actually similar to what we do with a QFT or a discrete Fourier transform. So this is similar, except that this is a polynomial case. This is similar to a Fourier transform. Because then, if we now define this term omega, and I'm just going to set in this as a common term of I divided by n here, then we could now, if we look at what we did in the previous case, this would simply be given by e to the power of 2 pi I multiplied with 0 divided by n and multiplied by 1. And this is then equal to 1. If I look at the x0 squared, this is equal to e to the 2 times 2 pi of I divided by n and multiplied with 0. So this is also going to be 1. And this would continue if I now look at x1, 1. This is now going to be equal to e to the power of 2 pi of I, and then I have 1 divided by n. This is also equal to 1. But if I then look at, no, sorry, that is actually not equal to 1. That is equal to my definition of w. And then I have my xi squared. So this is going to be e to the 2 pi multiplied with 2I divided by n. And this is going to be w squared. And then we could continue like this. And in that case, we could set up, if we now think in terms of the Fourier transform. So this is not the van der Monde matrix, but this is actually our Fourier transform. What we would have then is a matrix which looks like this, with 1s here, and then I have ones here. But then I get this omega, I get omega squared, I get omega cubed, and this goes all the way up to omega n minus 1. Here I would get, for the second one, I would get omega squared, and then omega to the power of 4. And this would continue up to 2 times n minus 1. So this is a transformation I would get if I write my Fourier transform, the discrete Fourier transform, in terms of a matrix a la van der Monde matrix. So if I just plug in these different terms here, because the terms which you see here would then correspond to the terms which we would have in the Fourier transform, where we now are looking at these specific terms. So for every such term here, we can now write the specific matrix elements in the unitary transformation. And this goes all the way down to omega of n minus 1. And finally, we would have omega of n minus 1 to the power of 2. So I'm going to give you a small exercise, which I guess everybody can do in a break here, unless you want to have a break. So the exercise is to find U inverse, because you can also show here in a pretty straightforward manner, and we will do that after the break, is that U minus 1, and you will see that it has actually a pretty simple expression, is actually going to be given by 1 over n, and then I have a sum from L equals 0 up to n minus 1, and then I'm going to have W of J L. I'm going to specify a little bit later what that is, and then I'm going to have a W of minus LK, and this is going to be given by 1 over n, and then I have a L equal to 0 of n minus 1, and I'm going to have a J minus K multiplied with L, and my omega is nothing but this E of 2 pi of I divided by n, and this term which you see here is equal, so I'm going to leave this as an exercise, is equal to 1 only if J is equal to K. So these are just some mathematical properties, which means that this is a unitary transformation, which also obeys this orthogonality here. So I'm just leaving that as a small exercise. And the basic transformation which we will be looking at is something which runs like this. And when it comes to the quantum Fourier transform, so these are just basically the discrete Fourier transform, classical ones. When it comes to the quantum Fourier transform, it's going to look pretty close to this, but we are going to manipulate the expressions so that we can implement that easily in terms of a quantum circuit. But these are just some basic properties of a discrete Fourier transform. And these are unitary / orthogonal transformations, which means that they have to obey orthogonality requirements. And these orthogonality requirements, when we look at the specific element, J has to be equal to K, because this matrix, when I take the matrix U times U of T, or complex, since it's complex, we should obey this relation here. So in the lecture notes, you will find elaborations along these lines, the solution to that exercise, but I'm taking the liberty of not going through all these details. I hope you can forgive me for that, but that's an exercise on testing the orthogonality of the transformation. So these are unitary transformations. So after the break, we're going to set up the basic mathematics for the quantum Fourier transform. And then next week, we are going to look at how we can implement these as circuits. And then we are going to derive the quantum phase estimation algorithm. And then till the Easter break, we are going to try to wrap up this so that those of you who want to follow that path, you should have enough information to both implement the QFT and the quantum phase estimation algorithm. And then after the break, we may discuss quantum machine learning algorithms or other topics of your interest. So just send me suggestions for what you would like to hear about. So welcome back, and we are now going to look a little bit more in detail into the quantum Fourier transform, and hopefully everybody can see my whiteboard here. So when we now look at the QF, nope, not that one, but this one. So when we now look at the QFT, we are going to introduce some short notations. So this is the QFT part. We are going to have n qubits. And if I have n qubits, that means that I will have 2 to the power of n, since this is a binary system, number of basis states. So that means that I'm going to reserve the letter n here to this number 2 to the n. So the lowercase letter is the number of qubits, and the uppercase letter is now the number of basis states, realizations which we can make. And if we just remind ourselves and we wrote n equal to 1, then we know that n is equal to 2 to the power of 1. And in that specific case, we have the states 0 and 1. If we, just as a reminder, look at n equal to 2, then we know that n is equal to 4. And the basis states which we made then were 0, 0. So these are tensor products, 0, 1, 1, 0, and 1, 1. So then you see these are the 4 states which we get. Also, these transformations which we are going to look at, y, as a function of u of x, these are going to be transformations which preserve orthogonality. So u preserves orthogonality. And it's also in our case going to preserve the norm. And you can quickly see that if you calculate if you define that xi, so these are 2 vectors now of xj. Now let me just take away the vector sign because I use only that one if I don't have this physicist notation. So this is going to be given by yi, and then I have u times u of, sorry, not that one. The opposite, sorry here. So this is y of I, y of j. This is a transformation, and I have my x of I transformed acting on x of j, and I have defined my original basis to be normalized and orthogonal. And that means that if I now remember that this just gives me the identity matrix, then I have delta ij. Now the QFT is linear, as most of the things we do in quantum mechanics. Is a linear operator, is A, linear operator, and that transforms an orthonormal basis into a new orthonormal basis. That's the way you can think of it. So there's a linear operator that transforms an orthonormal basis, an ONB, this is the acronym which we used previously as well, into a new ONB. So we saw the example with 1 qubit. So let's look at the example now with 1 qubit and 2 qubit. So the first example is the one we have seen before, 1 qubit. In that specific case, what we are doing now, we have a state j, which now is being transformed from another state. So we have n, which is the total number of states we have, of a k equals 0 up to an n minus 1. And then I have a e of I of 2 pi of j multiplied with k divided by n. And then we have a state k here. So if we look at the 1 qubit case, then we will have two states, 0 and 1. So if you think of this in terms of the so-called block sphere, so we have one state which points up. So the 0, 1 was what we label as a north pole. And then we have the 1 state which points down. And these are the eigenstates of the Pauli Z matrix. So what we are doing then is now to perform a transformation where we get a new state 0, which is simply 1 over square root of 2, which is the number of possible states I have. And the sum goes from k equals 0 up to 1. We have only two states. And now I have an e of 2 pi of I. I have 0 multiplied with k divided by 2. So the 0 comes from here. So this is a specific component which I'm setting up here. And that is given by k here, and which then gives us 1 over square root of 2. And then I have the state 0 plus the state 1. If I then look at this transformed state, I just put a tilde on it, and I do the same exercise again here, then I have a sum over k equals 0 of 1 of e to the 2 pi I multiplied with 1, k divided by 2, and k. So this is going to give me 1 over square root of 2. So the first term has k equal to 0. So that simply gives me 0 here, plus e to the pi of I multiplied with 1. And if we look back at that, that gives us essentially the same thing which we had before, except that now we call this the Hadamard gate, because this creates a linear superposition of the state 0 and the state 1. So if you now started with the state 0, the new state 0 is a linear superposition of 0 and 1. And the state 1 is now a linear superposition of 0 and 1 here. So if you look a little bit closer, then you can define a new state y in terms of u times a state x, which is the original state, and where u is simply given by the Hadamard gate. So I try to distinguish with a more fancy h when I have the Hamiltonian, as you may remember from the different exercises we have in connection with project 1. So this is nothing but 1 of 1, and then I have an e of pi of I, and that's the same as 1 over 2, 1, 1, 1, minus 1. So you could start now with 0, and then you perform a transformation. We now obtain a superposition of 0 and 1. So that means that you moved from your north pole to another point on the block sphere. So when you think of the encoding now, this is the thing which becomes a little bit interesting for us. Because if we now go to, when we are going to look at these different states here, we may like to encode them in a more compact way. So everything which we are going to deal with now rotates around a compact encoding of this information, okay? So let's look at the case with 2 qubits. So let's take a new example. Now we say n is equal to here, which means that the total number of n is 2 to the power of 2, which is equal to 4. We know then that we have the states 0, 0. We have 0, 1, which is the tensor product of 1, 0. I'm just reminding you of the more compact notation we have. And that becomes 0. And then we have 1, 0, 0. Then what we have next is 1, 0. And finally, we have 1, 1. So if we look at that one, we would now like to encode this in a smarter way. So we would like to have a compact encoding. So that you can retrieve the information about that state without storing the 2 qubits. So what I want to do now, if you look at this state here, I want to relabel this as state 0. I take the state 0, 1. So this is my hierarchy. And I want to relabel that as state 1. I take the state 1, 0. This is my third state. Starting with 0, it becomes 2. And the final one, I want to relabel that as state 3. Okay? Yeah. Yeah. This is what we are doing now. So we are going to use a binary encoding here, which we will then use when we set up the Fourier transform. So everything here is just a technicality, a boring one, but it's a technicality of retracing which component links to what. So if you look at the 0, 0, so let's take the 0, 0 term. And we said that we want to rewrite that one as 0. So if we take the first qubit, so we can have a hierarchy now in a bit basis, multiplied with 0, plus the second bit, 2 to the power 0, multiplied with 0. And if we look at this, this gives 0. If I take 0, 1, I want to encode that one as state 1. And now you see that this one can be rewritten. So this one would be 2 to the power of 1 times 0. And then the next ones, I would have plus here. So this would give us that one. And this gives us this one. So there's an ordering from the left to the right here, as well. And you can always change that ordering. And then we would have 2 to the power of 0 multiplied with 1. And you see that that becomes 1 here. And then if you do the next one, you will see now that if we take that state, so let me just do that. Then if we do the next one, we get 1, 0. When we want that one to be state 2 here, then we see that 2 here, this means that we have 2 to the power of 1 multiplied with 1, plus 2 to the power of 0 multiplied with 0, and that's equal to 2. So in this case, I have that bit in here, and then I have this bit in here. And finally, we have 1, 1, and this is something we want to be state 3 in our hierarchy. And we see immediately that we have 2 to the power of 1 multiplied with 1, plus 2 to the power of 0 multiplied with 1, and that gives us 3. So then we retrieve number 3 from that kind of hierarchy. So let's do another example so that we get some good feeling of what is going on here. So if we now take an example with 3 qubits, then we know that the total number of states is 2 to the power of 3. So we have 8 states, and the states would then be 0, 0. We would have 0, 0, 1. And now it depends on how we organize them, because we could have the next state, which could be this one. And then it would continue all the way up to 1, 1, 1. So suppose now that we look at the state in this specific hierarchy, which we have. So I define now a state which is equal to state number 4, and I want that one to be equal to 1, 0, 0. So that state which you have there is actually going to be given by the following. So it's 0, 1, tensor product with 1, 0, and tensor product with 1, 0. And I have in my hierarchy, this is state number 4. The way I now reshuffle the bits, you can always rearrange them, but then you would break this nice rule which we are setting up now. So this would be a state which runs like 0, 0, and then we have 1, 0, 0, 0. And you can see now that if you look at this specific case, I have 2 to the power of 1. Sorry, 2 to the power of 2, which is the leftmost bit. And we have 3, so that comes with a power of 2, plus 2 to the power of 1, multiplied with 0, plus 2 to the power of 0, multiplied with 0. And this one, so this one goes in here. This one is obviously in here, and that one is in here. And this becomes equal to 4. And that is the number which I want to represent that specific state. So this is just a kind of a hierarchy which we are setting up. So this means that in general, what we are going to have, so if we look at the general expression, so where we started, in general, we started with this expression. So we have a state J, which now for the 3-qubit case could be the states from 0 up to 7, 8 states. This is now given by 1 over square root of n. And it contains a sum from J up, no, sorry, a sum from K, n minus 1 of E of 2 pi of I of J times a K divided by n multiplied with a state K. This is the general expression. Now we can now rephrase our basis Y, a given basis Y or K. Let me just do that. So we can have a general basis K, which now can be given in terms of these states, K0, K1, up to some Kn minus 1. So if I now look at this type of information, which I'm going to set up, I could now define a new basis, Y, or J as I called it. So a J here, which now could be given by 2n minus 1 times J0, the first bit, plus 2n minus 2 times J1, the next one, plus, and this goes all the way up to 2 to the power of 1 of J of n minus 2 plus 2 to the power of 0 of J of n minus 1. So if we go back to that notation which we have here, or this kind of notation here, what I'm doing now is simply to set up a general state here, this J here, which I'm going to encode in terms of this representation here. So it means that I could now set up this basis states. So I'm going, if you look at this basis which we have here, this basis K, this is something which I can encode in. I simply assume that there is a specific basis which I have. So if I now look at this state J here, I can actually rewrite that one in terms of my original basis, which is a 1-qubit basis with different tensor products. So I would have 1 over square root of n. I have a summation here where I now just define a vector which I call for K0. Okay, sorry, K0 is equal to 0 up to 1. So I have only either bit 0 or bit 1. So I'm looking at my original 1-qubit basis where I take the tensor products. So if you go back a little bit here, if you look at this representation which I'm setting up here, I have qubit 1, which is just consists of bit 0 and bit 1, qubit 2, qubit 3, etc. So these are all tensor products. So this will be my basis states. So what I'm looking at now is a transformation of this state. So suppose now that your original state is this one, and now I perform a Fourier transform. So the new state, I started here, but then I'm actually here performing a Fourier transform of that original state. And this case are now the 1 qubit states. So that means that what I would get then is just a set of such operations. I would have a K1 equals 0 up to 1. I would have a K2, 0 up to 1, up all the way to a Kn minus 1, up to 1. And this is now multiplied with, and then I have e to the 2 pi I, and then I have my j value divided by n. And now I perform this sum from my k equals 0. And let's now just call this just differently. So I'm just going to call this an I equals 0 up to n minus 1. And then I have my coefficient, which I'm going to set up here, y of I. And then I have 2 of n minus y. Sorry, not that. Yeah, that should be it. So this should then be equal to 1 divided by n squared. So let me just write this out properly. So I'm going to have now different terms. So I'm going to have 1 divided by e of I of 2 pi j divided by 2 to the power of 0, tensor product with the next one, which is 1 divided by e of I of 2 pi I of j divided by 2 to the power of 1. And then this continues with different tensor products all the way in the final one, which is 1 divided by e of 2 pi of I of j divided by 2n minus 1. Because what I've used now is the following property. So if I look at a state like this one, of e of I of 2 pi of j divided by 2 minus k here, this is nothing but this specific state, 1 of e of I of 2 pi of j divided by 2k, 2 to the power of k. So what you have here, if you now look at this general expansion which we are setting up, we have now a tensor product of different states which have been operated on with something which looks like a Hadamard transformation. So if you narrow this down to examples, so if we now take the example with n equal 2, and then we look at 0, 0, and then we ask what that one is going to look like. So the transformation which we are going to do then, when we look at this specific transformation, that means that this is going to be transformed now as 1/2, because I have 2 qubits. So it's 1 over the total number of states, which is 1 divided by square root of 4. So I'm going to get 0. This is going to be given by the tensor product of 1, 1. So qubit 0, the first qubit, this one, transforms like you would have with a Hadamard transformation. Then I have to multiply this with the next one. So that gives me 1, 1 here. So if I look at this transformation, I start with a system which is in a state 0, 0, so that both qubits point north. Then I perform the Fourier transformation, and what I get then when I do the algebra is that this simply gives me 1/2, and then I have state 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. So I've now created a superposition. This is not an entangled state, but this is a superposition of the possible states which we have for 2 qubits. So that means that my 0, 0 state, through the Fourier transform, we can now write this as 0, 0 is now being Fourier transformed to a new state, which is now a linear combination. And in principle, what we have done in this specific case is actually to perform just 2 Hadamard transformations. So let's take a look at another example, just to get some feeling of what these quantum Fourier transforms are doing. So we take n equal to 3, and let's take the state. This is our initial state, 0, 0, 1. This is where we start. And then we perform now the transformation. And what I'm doing, so I'm setting up the transformation here. So I have 1 over square root of 8. Now the first state, 1, 1, which we are going to get, this comes from the state here, this one. And if you look back at these transformations, this is now going to be given by this term here. And since I have 2 to the power of 0, and then I'm putting 0 here, then I just get 1. So I have 1, 1. So that means that I will get a transformation here where we'll have 1, 1. But then the next one is going now to contain an exponential. So I will have a tensor product of 1. And then the next piece is going to be given by e of I of 2 pi divided by 2. And finally, I have the last tensor product, which now contains 1 and e of I of 2 pi divided by 4. So what I'm doing now, I'm simply setting up this more compact way of rewriting the Fourier transform in terms of all these types of operations. So if you then look at it, what this is going to give us is a new state, which is going to be given by 1 over square root of 8. So the thing which we have now is that this one is going to give us a complex number I. Another one is going to give a complex number. So this will give us -1 here. And this one is just going to give us e to the I of 2 pi divided by 4. And that is going to give us a factor of I. So this one is going to give us I. And this one is going to give us -1 because it's e to the I times pi, which is -1. So when I then plug in everything here and I perform the tensor products, I'm going to get 1, and I will have an I, obviously. And then I'm going to get -1 minus I, and then I have 1 and I, and now I'm squeezing in things here. So I should get -1, but then there should also be a -I here. Sorry for that. So these are the 8 components which we are going to get here. And if I write this state out, it's going to look a little bit more messy because we have 8 possible states. So this will be a linear combination of 8 different states. So if I bring everything together and if I've done my labeling correctly, this is now simply going to be given by 0, 0. And then I'm going to have plus I. And then I have my state number 1. And then I have the next state, which now gives me 0, 1, 0. And then I have minus I. And I have 0, 1, 1. And then I have plus. And then I have 1, 0, 1. I hope I put everything correctly together. 1, 0, 0. And then I have my minus 1, 1, 0. And this is minus I of 1, 1, 1. So let's do the counting now. So we have 1, 2, 3, 4, 5, 6, 7, 8 states. Okay. So if we now look at the case, go back to the case for n equal to 2. So for n equal to 2, then the whole matrix is going to look like as follows. My matrix U, it will be 1/2. And then I'm going to have, as we mentioned before the break, ones along the first row and the first column. And then we're going to have I. We're going to get -1 and -I. We're going to get -1, I, and -1, -I, -1, and I. And the coefficients which you're going to see then are actually, in general, we're going to have the following type of functions. So in general, what we are going to have then is a QFT. If we now have n equal 2 to the power of n states, so we're going to get a transformation matrix, which is going to look like as follows. Let me just remind myself a little bit. So it's going to have 1, will be a coefficient here, which is 1 over the square root of n. And this has 1, 1. So this is going to be like that, of 1, all ones here. And we will have 1 here, 1, and all the way ones here. And then here we are going to have W, and then we're going to have W squared. And this goes all the way up to W, n minus 1. We have W squared, W to the power of 4. And then we have W of 2 of n minus 1. And this goes all the way down to W of n minus 1. And then W of n minus 1 squared. And where this W is simply 2 pi of I, e to the 2 pi of I divided by n. So this is the way we can now set it up if we use a integer bit representation. Now, what is normally done is actually to use a floating bit representation. And that's going to give us a slightly more compact notation. So let me just wrap up this lecture today by giving you the floating bit representation. So we are now using integers like 1, 2, 3, 4, and so on. But it's pretty common now when you look at most of these algorithms to rewrite this with binary floats. So if you now think of the number which we set up, a given number to recognize the state. So we decided to define a state y, which is now given in terms of these different bits which we have, bit 1, etc., up to y of n minus 1. So that's one way to classify it. So the example was like for the 3-qubit case, we had a 0, 0, 1 as an example. So where y0 would be 0, y1 would be 0, and y2 would be 1. Now, what you could do now, since we know that this transforms, so this state here transforms like transforms in terms. So what we would have then would be 1 divided by the square root of n. And this is multiplied with 0 plus e to the 2 pi I. And then I have my y here. And then I have my 2 to the power of 0 multiplied with 1. Tensor product with 0 plus e to the 2 pi of iy divided by 2 to the power of 1 multiplied with 1. And this is then finally, when we go through all the tensor products, we end up with 0 plus e to the 2 pi of iy divided by 2 to the power of n minus 1, and then multiply with 1, etc. And then we could decode these y's in terms of y0 of 2 to the power of n minus 1 plus y1 to 2 to the power of n minus 2, and all the way down to yn minus 1 times 2 to the power of 0. So this specific state, which we now, for, let's say, in this notation, gave the label of state 1. If we had 0, 0, we would label that as state 0 here. This would now be state 1. And then we would simply use this full notation to decode and find number 1 according to this formula here. And then we use the integer representation, the binary integer representation. But it's pretty common to actually use a binary float representation. So as I promised, this is not the too exciting topic which we're going through, but I just wanted to show you the type of notations which we end up using when we are going to implement a QFT next week. So instead of using the binary representation for this specific number, so like in this hierarchy, if you have the state 0, 0, 1, this 1 here will be 1, this y, but the y's which you have here are now referring to the y's for these numbers which you will have in here. Okay? So it's a little bit back and forth here, okay? And the final thing we're going to do now is just to introduce binary floats. In that case, suppose now you just have a binary number. So if you now look at the state which we have, a binary float would then be given by 0. We have some y of k plus 1, all the way up to y of n minus n. And that will be given by y of k, the first one, times 2 to the power of minus 1, plus y of k minus 1 of 2 to the power of minus 2. And this goes all the way down to y of n minus 1. And then we have 2 to the power of minus n minus k. And this number n is larger than k here. So if you now look at a specific example with n equal to 2, just to get a little bit acquainted with this notation, then we would have a 0 and y1. And that's simply y1 divided by 2 if we use this formula. And then I have a 0 and y0 and y1. And that is simply y0 divided by 2 plus y1 divided by 4. Now, our qubit state then, this y, is now going to be given by y0 and y1, where they can be either 0 and 1. And if I now encode this, I will get a notation which is going to look like as follows. So let's just wait a little bit so everybody can write it down properly. Because the general way by which we would encode this is now something which changes a little bit. So we would get this one equal to 1/2. So this is a transformation which we are doing. So let's now not an equal equality sign here, but this is going to transform as 1/2, and then I have plus, and then I have e of I times 2 pi, and this contains now 0 and y n minus 1, which in our case is actually 1. So let's just write that one, y1, multiplied with 1 here, And then this is, we take a tensor product with 0 plus e of 2 pi of I, and then I have 0, and then I have y0 and y1. So this is a little bit more compact expression than the one we had previously. So if I then choose 0, 0, and then I just plug in the expressions, what we are going to get then is simply 1/2. And then I'm going to get 0 plus 1, tensor product with 0 plus 1, as we had before. So this is going to give us the state of 1/2 of 1, 1, 1, 1. The general case, the way we are going to encode this is as a Fourier transform which runs as follows. So if we take a state y, which is now given by these original qubits up to yn minus 1, this will transform with our quantum Fourier transform. The compact expression is now given by a transformation which looks like 2 to the power of n. And I have the first one, 0 plus e to the I of 2 pi, 0, yn minus 1, multiplied with 1. Tensor product with 0 plus e of I of 2 pi I, 0 of yn minus 2, and then I have yn minus 1, multiplied with 1. And this goes all the way down to the full one, where we have 0 plus e of 2 pi I, and then I have 0, and then I have y0, y1, y2, and up to yn minus 1. And you will see quickly now the reason why we introduce this notation instead of the integer notation. And the reason for that is pretty simple, because with this notation here, if you look closely at it, what you will see now is that this notation contains the factor of 1/2 to the power of something. So if you look back at the original notation, we were carrying with us y divided by 2 to the power of something. So this factor here can be simplified by switching over to binary floats. So instead of us carrying with us the original y state here and to the divided by the power of something, we simply switch from this notation here to this notation here, where now the y divided by the power of 2 to something is automatically included. That's the main reason. So it's a more compact notation where you now don't need to include and take care of 2 to the power of something, but you have it automatically in the binary float representation. So these are just compact ways of rewriting the same type of information. So these are the expressions which we need when we now are going to set up the quantum circuits next week. And I see I'm running over time here, but I wanted to go through these kind of exciting technicalities so that we have everything ready next week so we can set up circuits for the quantum Fourier transforms. We can look at some code examples, and then we are going to look at the quantum phase estimation algorithm. And we will then also look at practicalities till we reach the last lecture before the Easter break. So next week it will be Wednesday the 2nd, and then we have Wednesday the 9th of April. And then there's obviously a break, but then hopefully you've seen both the quantum phase estimation and the quantum Fourier transform so that you have enough material to actually encode this as parts of project 2, if you want to do that. And after the break, depending on your interests, we can discuss either adaptive EQE, other methods, or quantum machine learning algorithms. So this is very much up to you guys. Just send me your interest, wishes, and etc.